studying the emergence of relativistic astrophysics. It's really a huge topic, and the story I will tell you is some way that I consider them my preliminary results, but it's my way into this really huge topic, and I hope it will be some way there will be occasion to discuss and to reflect on this. You will excuse me, but I will read in order to be sure to keep the time. And in particular, I will follow a path tracing the main steps in the evolution of research on superdense matter, performed since the mid-20s, and show how theoretical investigations on such a basic problem, accomplished at the intersection of different theoretical frameworks and involving several disciplines and sub-disciplines, had actually a guiding role in the evolutionary process that led to the emergence of relativistic astrophysics. The fundamental and basic character of the concept of dense matter materialized in different realms and provided a context for reasoning on extreme conditions spanning from real stars to theoretical astrophysical objects up to models of the early condensed universe envisioned by Lemaitre and inspiring in turn further developments. As John Wheeler himself emphasized in spring '68, no test of Einstein's theory is more dramatic than the expansion of the universe itself, and none has a closer bearing on the phenomenon of collapse. And in fact, these two fascinating phases embedded in Einstein's equations are related to many different realms of research, all designing the rich tapestry from which emerged the multifaceted science of relativistic astrophysics. A pivotal aspect that can be identified along this trajectory, which is in retrospect is actually not surprising, considering that this story is invaded by boundary problems, is the key role of a group of scientists working within overlapping but different scientific cultures, who provided the necessary cross-fertilized soil for the emergence of new basic ideas or tentative theories. This was characteristic of many scientists who lived the pioneering period going from the 20s to the end of the 30s and who guided physics through the war years up to the late 50s. Typically, these people were at ease in different fields and were accustomed to a global and transdisciplinary view of physics. After the war, also thanks to scientific developments and technological advances stemming from war and post-war scientific activities, the confluence of several strands of research created the necessary multicultural context in which astrophysicists were able to recognize that physical processes exist in the universe in which considerations of general relativity have a dominant role, or even that are understandable only in terms of Einstein's theory. My overview will be for obvious reasons, very schematic, and far from being detailed, mainly basing on qualitative physical concepts. I had to cut out many minor contributions that are part and parcel of this scenario, but I hope that all the same to be able to provide a material for further reflection and discussion. All this began during the first half of the 20s, when Arthur Eddington brought the remarkable properties of white dwarfs to the attention of the astronomical world. In 1924, he argued that in the hot stellar interiors, all the electrons would be stripped away from their nuclei. In this case, there was nothing to prevent the free electrons from becoming closely packed with the bare nuclei, and densities as high as 1 million grams per cubic centimeter were imaginable. Eddington also worked out the magnitude of the gravitational redshift which would be expected from such compact star according to general relativity, which was measured by Adams in 25. In his book, Internal Constitution of Stars, from many years a Bible in the field, Eddington remarked that the stellar material can remain at high density only so long as it is ionized, and it stays ionized so long as random collisions prevent recombination. But at zero temperature, all random motion should cease, and nothing should prevent electrons and nuclei from recombining. The star would need to expand 10,000-fold to accommodate the volume of its neutral atoms. Where would it find the energy to do this if its available fuel had been exhausted? Direct supervisor, Ralph Fowler, a real expert in statistical mechanics, promptly tackled Eddington's conundrum and was able to explain the nature of the hydrostatic equilibrium of white dwarfs, pointing out that the electrons in white dwarfs form a highly degenerate gas obeying Fermi Dirac statistics, and hence, at a given temperature, their pressure would be greater than the thermal component. It is remarkable that this was most likely the first application of the Fermi Dirac statistics to a system of degenerate fermions. In 1927, Arnold Sommerfeld applied the Fermi statistic to electrons in metals. Several researchers studying quantum theory in condensed matter were thus led to extend their reasoning to the most extreme conditions in stars. In 1928-30, the Thomas Fermi gas model was used by Frenkel, Anderson, and Stoller. Stoller was at the time Fowler's student, to calculate the relationship among the mass, radius, and density of the white dwarf stars, assuming them to be essentially homogeneous spheres of a relativistic electron gas. Both Anderson and Stoller soon showed that a star can contract only until the decrease in gravitational potential energy becomes insufficient to balance the increase of the kinetic energy of the electrons. Accordingly, for stellar masses larger than about one solar mass, there can be no equilibrium white dwarf configurations. Chandrasekhar himself was led to build studies in reading Gallic proofs handed him by Sommerfeld on electrons squeezed together into small volumes, in a metal, for example, instance, and in discovering Fowler's fundamental contribution. Without knowledge of Anderson and Stoner's works, Chandra derived the equation of state of a degenerate gas in the extreme relativistic limit and found that in this limit the mass of the white dwarf is uniquely determined. It was just a little bit more than a solar mass. He then studied the equation of state of white dwarf matter over the entire range of densities, arriving at the conclusion that a star of mass larger than the critical one cannot pass into the white dwarf stage, and one is left speculating on other possibilities. In 1935, during a meeting, hot meeting at the Royal Air Society, Eddington attacked Chandra's results, considering it a reductio ad absurdum of the relativistic degeneracy formula. And actually, he correctly describing what would happen putting further Chandra's ideas and rejecting very strongly them. Actually, I cannot go into this, but it was a really very hot debate. Actually, it was generally thought up to the early 60s that there must certainly be a way out of this situation, extreme situation. Presumably, every massive star would eject enough matter into interstellar space to reduce its mass below 1.4 solar masses and thereby enter a safe white dwarf grave. By the mid-30s, the theory of the fundamental properties of white dwarfs had been developed. Thus, astronomers and especially physicists had at disposal a new physical system, a state of matter that could be investigated only in terms of the new 20th century physics. While Chandra and others were theorizing on dense interiors of white dwarf stars, the Belgian astronomer and cosmologist Georges Lemaitre, using general relativity, was formulating the first example of a universe evolving from a condensed material pre-universe and not from a singularity in space-time. He proposed in 1931 that the Friedman model of universe had evolved from an initial state that he termed a primeval atom, consisting of an immense number of protons, electrons, and alpha particles, packed together at nuclear densities. At that time, a remarkable article appeared in June of 31 by Langer and Rosen, postulating the existence of the neutron, a combination of an electron and a proton, and used it to reason on the interior of stars. It was the old Rutherford idea circulating since 1920, but probably for the first time was applied to astrophysics. A milestone in this story is Landau's influential work, submitted before the announcement of the discovery of the neutron. He criticized the astrophysical methods usually applied in attacking the problem of stellar structure, characterized by making physical assumptions chosen only, as he said, for the sake of mathematical convenience. It seems reasonable, he said, to try to attack the problem of stellar structure by methods of theoretical physics, that is, to investigate the physical nature of stellar equilibrium. On this general line, we can try to develop a theory of stellar structure. The central region of the star must consist of a dense collapsed core, which would permit stars to shine for far longer periods than the contraction of less dense star permitted. As matter from an outer shell fell into the core, it would liberate energy in vastly greater amounts, said Landau. However, applying the relativistic theory, Landau argued that theoretically, for stellar masses larger than 1.5 solar masses, there exists in the whole quantum theory no cause preventing the system from collapsing to a point. As in reality such masses exist quietly as stars and do not show any such ridiculous tendencies, we must conclude that all stars heavier than 1.5 certainly possess regions in which the laws of quantum mechanics and therefore of quantum statistics are violated. This was Landau's conclusion, also based on, at that time, Bohr was postulating non-conservation of energy in the nuclear realm that was still formed by electrons and protons. The coming of age of nuclear physics, officially starting in 1932 with the discovery of the neutron, inaugurated the second phase in the expansion of this knowledge network. During this period, that ended with the outbreak of World War II, it was realized on theoretical grounds that the compression of sufficiently dense matter during stellar evolution would induce neutronization due to electron captured by protons. The interior of stars transformed into a dense gas of neutrons and became a model for theorizing on nuclear matter, the new frontier of microscopic physics. A number of ideas underlying Landau's model and Stern's analysis found their way into 20th century astrophysics. Combined with the already circulating idea that stellar explosions were associated with collapse to a superdense configuration, probably inspired Bari and Spitz-Inside in 1933, end of 1933. With all reserve, we advanced the view that a supernova, the term was coined at that time by them, represents the transition of an ordinary star into a neutron star consisting mainly of neutrons. Such a star may possess a very small radius and an extremely high density. As neutrons can be packed much more closely than ordinary nuclei and electrons, a neutron star would therefore represent the most stable configuration of matter as such. At the time, this was considered an isolated speculation with no real physical theoretical background, also because of the divide between the different culture of astronomy and physics. Astronomers, moreover, were not interested in such an object which was certainly undetectable. Quantum mechanics and theoretical nuclear physics could be applied in the emerging field of nuclear astrophysics, whose object of investigation was also the synthesis of chemical elements in stars. A neutronic stellar nucleus of the Landau type might play a role in this kind of processes. In his very cited book, Atomic Nuclei and Nuclear Transformations, published in 1938, but the preface is May 1936, inciting Chandra 31 and Landau 32, Drummond showed that a gas of neutrons could be compressed to a much higher density than a gas of nuclei, and electrons analogous to the conditions inside an atomic nucleus. So you see the two parallel ways of reasoning. physicist, nuclear physicist, and Zwicky idea of the neutron star. That the subject of dense matter was gaining some momentum can be inferred by a very detailed review article by Hunt, appearing in 36, specifically discussing the interest of investigation of dense matter in stars for physics, for fundamental physics. In October 37, the Indian astrophysicist Carteri was the first to explicitly introduce the neutron into the theory of interior of cold degenerate bodies like white dwarfs. Degeneracy, in the case of neutrons, rather than of electrons, leads to even smaller volumes. The density of such systems could thus be of orders of magnitudes greater than in the case for white dwarfs. Was it possible that such gigantic cores of superdense neutronic matter might be at the origin of stellar energy? What is in fact emerging from research of the pre-World War II years is the catalyzing role played by a long-standing and challenging question for theoretical astrophysics, the source of energy stars. Between 37 and 38, another influential paper by Landau. When I say influential, this means that all these articles, all Landau articles were cited during the years, even after many years to come, appeared addressing the problem of stellar energy. Landau jumped from his pathological course of 31 and related unknown physics to neutron cores described by standard nuclear physics. In citing Hund, Landau started from the state where all the nuclei and electrons have combined to form neutrons. When the mass of the body is greater than the critical mass, then in the formation of the nucleonic phase, an enormous amount of energy is liberated. And we see that the conception of a neutronic state of matter gives an immediate answer to the question of the sources of stellar energy. Landau finished his new paper with an appeal to build up the models of such stellar objects. I want to recall here that at that same time Landau was imprisoned, as you well know. And he wrote this article in order to avoid prison, apparently. The fourth Washington Conference on Theoretical Physics, organized by Gamow, Teller, and Tuve, was devoted to problems connected with the source of stellar energy, a hot problem both for nuclear physicists and for astronomers. At this conference, Hans Bethe was inspired to investigate those processes that produce energy in stars. Landau articles on neutron cores in the 19 February 39 issue of Nature did not escape Oppenheimer's attention. Coming from Fritz Zwicky, the idea of a neutron star as the energizer for supernova was in Oppenheimer's view a mere speculation. Coming from Landau, a neutron core as energizer for a normal star was worthy of a serious thought. Inspired by Gamow and Landau's work on a condensed neutron core, Oppenheimer tackled the problem of the stability of such highly degenerate objects together with his collaborator Robert Server. Interest in such stellar models declined when they showed that one cannot build a viable model of the sun with its energy coming from a neutron core, and in particular when Bethe published his breakthrough theory outlining the main thermonuclear processes underlying the production of energy in ordinary stars. However, Oppenheimer continued to be interested in studying the problem of stability of stellar cores. Inspired by his friend, the relativist, Richard Tolman, and working with his student Volkov, Oppenheimer tackled systematically within the framework of Einstein's theory the problem of the stability and final fate of highly compact massive neutron cores that cannot withstand the tendency to collapse into themselves under the influence of their gravitational fields after having exhausted their nuclear fuel. In February 39, the Oppenheimer, Volkov, and Tolman's articles appeared within the same issue of the Physical Review. They said, Volkov, Oppenheimer, it seems of interest to ask whether this model of the final state of a star can be run for arbitrarily heavy stars. That is, to investigate whether there is an upper limit to the possible size of such a neutron core. Oppenheimer and Volkoff analyzed numerically the equilibrium configurations of a star built up from an inner neutron gas. For this purpose, they employed for the first time the general relativity equations of hydrostatic equilibrium. But now that he had begun to think about neutron stars, Oppenheimer was drawn inexorably to the issue. What precisely is the fate of massive stars when they exhaust the nuclear fuel that keeps them hot? At that time, Gamow and Chandrasekhar too were speculating on the same question, so Oppenheimer was not alone. But it were Oppenheimer and Snyder who investigated the issue of collapse to its extreme consequences. The maximum mass of a neutron star was calculated by Oppenheimer and Volkoff to be 0.75 solar masses. This discovery motivated Oppenheimer and Snyder to study what would happen to aggregation of cold matter with mass in excess of this limit, and showed that Einstein's theory of general relativity compares any massive star that has exhausted its supply of nuclear fuel to enter a state of permanent free fall. A parallel reflection on the collapse, we are in 39. A parallel reflection on the collapse problem had been Dutt's contribution of 38, using general relativity to examine the final fate of an idealized massive matter cloud. Zwicky himself, between 38 and 39, had again investigated the theory and observation of collapsed neutron stars in connection with his theory of supernovae, also using general relativity, because he had discussed the derivation of his results with Tolman. He interpreted the large red shifts observed in the spectra of the recent bright supernovae as gravitational redshifts. He also made a very interesting comment that I want to read, considering that it was made at the end of the 30s. The general theory of relativity, although profound and exceedingly satisfactory in its epistemological aspects, has so far practically not lent itself to any very obvious and generally impressive applications. This unfortunate discrepancy between the formal beauty of the general theory of relativity and the meagerness of its practical applications makes it particularly desirable to search for phenomena which cannot be understood without the help of the general theory of relativity. According to Cernuschi, the hypothetical transition from the dilute to the condensed neutron phase afforded a complete physical basis for the idea advocated by Zwicky that the supernovae originate from the sudden transition of an ordinary star into a centrally condensed one. In 1939, Einstein himself published a paper analyzing quasi-static clusters of masses moving on circular orbits and worked out how they would behave as they collapsed through gravity. But basing on his calculation, he asserted that Schwarzschild singularities do not exist in physical reality. It's interesting to look at the parallel Zwicky's opinion. It is impossible to observe physical conditions in stellar bodies which have reached the Schwarzschild limit. Now I have read a list of what roughly happened during war and early post-war years. I don't want to enter into this ocean which is related to cosmology, models of the universe, origin of elements, a stellar evolution. I'm listing this topic tackled during this period just to recall the ubiquitous presence of the question of dense matter and its being intermingled with this scenario that was on the verge of becoming more complex during the 50s with the arrival of radioastronomers as new actors in the world stage. I want just to emphasize that Pascual Jordan too was interested in dense matter in stars, and he wrote 3 articles on this problem. During the post and Cold War period, renewed interest in the investigation of highly dense matter, stellar matter, and on the abandoned problem of gravitational collapse within Einstein theory was brought about by implosion and explosion problems related to the design of thermonuclear weapons. Further progress necessitated better knowledge of nuclear structure and nuclear interactions, respect to what had done Oppenheimer and collaborators. New tools, typical of post-war science, were now available. The impressive advances in nuclear science, combined with the first powerful computers, designed to perform the complex calculation for thermonuclear weapons, and now used to calculate the equation of state of condensed stellar matter up to the endpoint of thermonuclear evolution. In the 50s, two physicists, in particular John Wheeler in the United States and Yakov Zedlovich in the Soviet Union, emerged from their respective hydrogen bomb efforts and took up where Oppenheimer and his collaborators had left off in 1939 at the outburst of the war. These scientists and other groups all over the world inspired a new generation of young theorists. From Wheeler's autobiography, in January 1952, Wheeler had studied Oppenheimer's papers concerning with gravitational collapse. But he said, but I was convinced that nature abhorred the singularity. I carried this conviction with me for many years. If I was going to fight against the idea of true singularity, I had to understand the enemy. I had to have general relativity to my arsenal of knowledge so that I could explore that new domain of supercondensed matter where both relativity and quantum mechanics might share the stage. That's why I wanted to teach the course, and in fact it began a course of general relativity. What I learned in teaching the course was that the riches of Einstein's theory had been far from being fully mined. Wheeler's path into general relativity is a very articulated one. Here I want only emphasize his interest in the investigations on what is still one of the major challenges of relativistic astrophysics, namely the equation of state at the center of a superdense star. Assembling all the available theoretical information, Harrison and Wheeler constructed a semi-empirical equation of states for matter in its absolute ground state to the endpoint of thermonuclear evolution at all stages of compression up to supranuclear densities. Using this, Bacano performed 44 numerical integrations for different choices of central density of the general relativistic stellar equilibrium equations on Princeton's Mania computer. The resulting plot of mass versus central density was a curve with two humps corresponding to the white dwarf and neutron star configurations. The Chandrasekhar and Oppenheimer's Volkov results were confirmed and for the first time brought together into a single overall picture. This work was presented by Wheeler and his collaborators at the Survey Conference of '58, dedicated to the structure and evolution of the universe, the first Survey Conference devoted entirely to astrophysics that gathered some of the most distinguished astronomers and experts in cosmology and general relativity. It was the first of this kind within the Survey series, establishing an official connection between astrophysics and general relativity. During the Survey Conference, the Russian astronomer Ambert Sunyan suggested that the radio galaxies are systems in which ejections from the nuclei of tremendous scale take place. As a consequence of such ejections, clouds of high-energy particles are formed. And in fact, since the early 50s, synchrotron radiation of ultra-relativistic electrons gyrating in interstellar magnetic fields was recognized as a source of radio emissions, especially by Russian scientists. According to this proposal, Ambert Sunyan was very prescient in rejecting the idea that the nucleus of a galaxy is composed of common stars alone. He said, we must admit that highly massive bodies are members of the nucleus which are capable not only of splitting into parts that move away at a great velocity, but also of ejecting condensations of matter containing a mass many times exceeding that of the Sun. 58. At the Survey Conference, Fritz Hoyle had presented a talk on the steady-state theory and one on the origin of the elements in stars, and also discussed on the supernova explosion. And in fact, in the first half of the 20th century, cosmology was considered an esoteric field, but the problem of origin of elements triggered a new revival of interest. A natural connection was established with nuclear astrophysics, a fast-developing field at the intersection of various subfields of nuclear physics and astrophysics. At the same time, the problem of nucleogenesis rekindled interest in neutron stars. As possible remnants of supernova explosions, these very dense objects might also play a role in the formation of chemical elements in stars that was a major issue in contemporary models of the universe. Problems of stellar structure, stellar energy generation, and stellar evolution were being studied on a more realistically physical basis than before. Neutron capture cross-section were now available as a byproduct of the nuclear physics programs carried out during the Second World War. Attempts were also made to determine more precisely the composition of the neutron star, including not only such essential particles as protons and electrons, but also mesons and hyperions. During the 50s, the climate of debate between different universe models extended to the realm of radioastronomical research. The development of radioastronomy had opened in the 50s a new technological window. Its practitioners mainly came from physics rather than from astronomy. Radio catalogs compiled in the mid-50s, basing on the development of new techniques, pointed to the inference that radio astronomers were studying the universe on a much greater scale than optical astronomers. New complete catalogs of radio sources showed that the number of intense sources increased with distance. This implied that galaxies produced more radio waves in the past, and thus began to call attention to the conflict with steady-state cosmology, according to which the observable universe is basically the same in any time as well as any place, thus leading to an intense controversy. In that same 58, the year of the Solvay Conference, reports at a large conference of radio astronomy in Paris, gathering 162 radio astronomers from 17 countries, were revealing a universe full of catastrophes and of radio sources emitting enormous amounts of energy, as opposed to the quiet optical universe of ordinary stars and elegant spiral galaxies. Prior to 58, nearly all astronomical observation could be interpreted in terms of the major observed constituents of the universe, ordinary stars and interstellar gas. The advent of radioastronomy obliged astronomers to realize that very much in the universe is of an exhaustive nature, and that violent events exist in galactic nuclei with tremendous release of energy. By the mid-50s, the correctness of the synchrotron hypothesis as radiation emitted by highly relativistic electrons by strong non-thermal radio sources was confirmed, and it became evident that it could be applied to other astronomical objects in which there was evidence for high-energy astrophysical activity. Thus, after the Paris Symposium, the enigma of the strong radio sources had begun to emerge in its true and colossal proportions. Mysterious energy sources exist in the universe, able to supply more than 10 to 60 erg, or perhaps even many times more than that, in the form of relativistic particles. In May 59, Geoffrey Burbidge estimated the total energy in particles and magnetic fields in non-thermal radio sources to account for the radio emission. The energies proved to be enormous, in some sources corresponding to a rest mass energy of 10 to 6 solar masses. Some astrophysical means had to be found for converting a significant fraction of the rest mass energy of a galaxy into high-energy particles and magnetic fields. In October 61, Ginsburg, who had formulated the synchrotron hypothesis, suggested that gravitational energy released in contraction might account for the radio sources. This is a preliminary idea. The migration of nuclear physicists and astrophysicists to the growing field of nuclear astrophysics was creating a new community that possessed the necessary interdisciplinary knowledge for tackling such unprecedented problems, also in connection with the related evolution of relativistic cosmology. Between 62 and early 63, William Fowler, who had been educated as a nuclear physicist, and Fred Hoyle, who had Dirac as thesis advisor and whose wide scientific culture would give it here for granted, were the first to propose a specific model suggesting that these huge outpourings of energies in distant galaxies could be supplied through the gravitational collapse of a supermassive star, the equivalent of thousands of supernovas, located in the center of the galaxy. Objections were later raised against this interpretation, of course, but alia iacta est, and the die was cast. At the moment, Fowler and Hoyle's view was strengthened by the optical identification and interpretation of the redshifted spectrum of quasi-stellar objects. The breakthrough came on February 5, when Schmidt identified the Balmer lines in the strange spectrum of the object 263, but redshifted by 16%. The quasi-stellar objects had unprecedented large redshift. If these were interpreted as being cosmological in origin, such mysterious sources were radio frequency emitters as powerful as the most powerful radio galaxies, and their optical luminosities were up to 2 orders of magnitude greater than those of the giant galaxies. All this raised a strong suspicion that the relativistic gravity might have a role in supernovas, in galactic cores, and in quasars themselves. Feynman appears at that time at the origin of 2 papers submitted in spring '63. Ivan on massive stars in quasi-static equilibrium using collapse arguments and GR, and Michael, collapse of massive stars, both within general relativity theory. Several crucial elements were now in place. Moreover, in '62, a Center for Relativity, headed by Shield, was established at the University of Texas. This contest triggered in June of that same '63 the decision taken by Shield, Schuking, and Peter Bergman to organize a large international conference, the first of this time. The many-sided and basic aspects of the question of gravitational collapse made it imperative to bring together optical and radio astronomers, theoretical astrophysicists, and general relativists for a thorough discussion on the newly discovered quasi-stellar objects. Roy Kell presented his recent words at the Texas conference, but only relativists were excited, and in fact his talk was not mentioned in the summary. There was a long way to go, still a long way to go. Nonetheless, these were the heartening words from Thomas Gold in his after-dinner speech. This, of course, is a historic meeting. It will be remembered as the meeting where these great new astronomical discoveries were first discussed. Everyone is pleased. The relativists who feel they are being appreciated, who are suddenly experts in a field they hardly knew existed. The astrophysicists for having enlarged their domain, their empire, by the annexation of another subject, general relativity. The term relativistic astrophysics was actually coined by the three organizers, and the field came into official existence, setting the stage for the actual beginning of a common dialogue. By '65, only a couple of years after the Texas Symposium, the field literally exploded. Dozens of articles were published on issues related to general relativity, neutron stars, and gravitational collapse, and it evolved quickly, also in connection with the evolution of X-ray and gamma-ray astronomy that were beginning in those same years. At that time, Zeldovich, with his collaborator Turnovnikov, had fully entered the stage of relativistic astrophysics. Penrose had published his extraordinarily innovative paper, the cosmic microwave background was discovered, and pulsars were just round the corner. Joe Weber would soon announce having detected gravitational waves, and the crew of the stellar ship Enterprise in a Star Trek episode soon had its first encounter with a black star. They call it black star in this episode. The black star in '71 was officially presented to the world as black hole by Wheeler and Ruffini, even if the terms appear to have circulated since the first Texas conference and perhaps even before. So those were the days leading to bridging the gap to the previous wonderful conference of Professor Ritz. I stop here and
thank you, Luisa, for just ending where your talk started. So we have, there's an intermittent, just to point out, we don't have a coffee break, but there is coffee available until 5 outside. Anybody wants to sneak out and sneak back in. I would emphasize the sneak back in part of this, but please feel free to take a coffee. So there is an occasion now, let's make it like 20 minutes or so for questions that you have to the two. Please, Professor Gensler, Luisa, if you come upstairs, like the room is in bed. So, and those who sneak out now, don't forget the sneak in part again. So, are there any questions to this?
I think they need more coffee than our wisdom.
Jim, you look like you have a question.
Yes. The Fermi-Dirac statistics were invented to account for the structures of atoms. Wasn't that well before we were worried about the structures of white dwarf stars?
This was really a timely application because it was 26, so really parallel with the coming out of the statistics. And it was actually, as far as I know, the first application of the statistics.
But the first application showed us atoms.
It was not really an application in the sense that they formulated it for atoms, but not as a. I would say that the application in the atom would be the Thomas Fermi model, some way, or an application within the atom. The statistics was more generic to fermions.
I think we're
Fermions in general.
Pauli principle and Fermi statistics, right? Yes. Right, but then Fermi statistics is the statistics obeyed by a thermal system. Particles of the sort of
I would have a question to Professor Gensler. So we heard a lot also during the talk of Madame Shofi-Ueha about how the field was divided between mathematicians, astronomers, physicists, whom it took a long time to really get together. And Luisa has shown us some of the processes, some of the meetings that brought forward the cooperation, and really also the difficulties. So I'm going to ask you now, how is it today? Is that still an issue in the field of relativistic astrophysics, disciplinary divides, or can we say this is only a matter of...
Absolutely, yeah. I mean, I think that the divide between the astronomy community and the physics community is still there. I mean, black holes are accepted, but for for most astronomers, that's a dealt with subject, so to speak. The issue is technology, and that's not what the physicists would say as we would.
Are there other questions? You put out, don't you? Thank you, that was fun.
Yeah, I found the description of the evolution of relativistic astrophysics very interesting, how things got sort of gelled in the 1960s. But it was still true, as I know from my own experience, that black holes, particularly, not so much neutron stars, but black holes were a concept that was resisted by astronomy for another 2 decades. It wasn't until we had X-ray astronomy, even though all the evidence pointed to them from radio astronomy and in quasars and other things, that it seemed to me that it was really until we had X-ray astronomy that people began to, in astronomy, began to accept that. Is that, would either of you like to comment on that sort of evolution?
Yes, I would say that 71 was also the year in which appeared the results of the Ururu satellite that really began to show the way to understand with very different tools this kind of processes related to black holes, to these compact objects and so on. So it was really X-ray astronomy that began to delve into this problem. That's true.
It's also a question of accuracy, right, of the measurement. So you know, beyond the phenomenological things of X-ray emission and so forth, in the end you would like to have a dynamical measurement, right? And so that's the binary star method. And of course, you know, unless you know the inclination, there you have your first uncertainty goes in squares. And the next one is that the early measurements of Cygnus X1, I believe, Jim, you probably recall that better, was sufficiently uncertain. Yeah, it was 12 plus minus 6 or something like this, that you couldn't be sure that it wouldn't, you know, still have a neutron star explanation. So these numbers came down over the years, and then you know, it could be still.
Okay.
No, just one. And in fact, I think that even before the discovery of pulsars, I think already in '64, someone had the idea of the binary idea in order to reveal something, in the sense that you have to have a system of that kind to see something that you could not see in absolute, to reveal in different means.
There was a question over here.
I just have a question about the debate between Eddington and Chandrasekhar. Was that really a debate, or was it more of Eddington basically publicly deriding Chandra's conclusions? Chandra was, I think, a student and much younger than Eddington, and Eddington wielded enormous influence. Could you speak to that? I mean, this is just based on some accounts I've read. I mean, if you have more insight into that, what was the nature of that reading?
It's clear that at that time Eddington was really a god, completely, and Chandra was a very young student. It was not a debate. There was a small debate between Chandra and other physicists. He involved other people, Bayes, Bohr, Möller, and they did agree with him. But of course, nobody publicly said something about it. So he retired. He was defeated, of course, in this sense. It was not a debate between him and Eddington. But at the time, the question was completely closed. So.
Thank you, Luisa. I think Dan had a question.
I'm just going to jump in on that and wonder if there wasn't a connection between the last couple of points, because it has seemed to me that Chandra did reach out to the physicists to say, surely we could put Eddington right here. And it did, I haven't studied it very carefully, but I wondered what your opinion was. It seemed a bit as if the physicists were a little reluctant to get involved in a debate on this astrophysical terrain.
That's clear.
Perhaps reflective of what we were talking about a moment ago, you were going to raise this issue of the separation between.
Even if Eddington was very respected, of course, as an astrophysicist, but there was a divide that we were talking about.
Maybe I make just a comment on Chandra. It was clear from the time of that debate with Eddington that if he was going to win this debate, he was going to have to investigate. He was going to have to work in general relativity. He was going to have to investigate gravitational collapse or something like that. Yet he didn't do that until the 1960s, and he kept, for a long time, he kept a year-end diary of his work. At the end of every year, he made notes. And sometime in the 1950s, he made a remark that he had talked to a number of physicists about whether he should switch into relativity and start doing work in relativity in the 1950s. And they all told him it was the graveyard for physicists.
Okay.
So he didn't. He waited another decade until he felt he was sufficiently well established, having done his work on magnetohydrodynamics and so on, to ignore the graveyard.
And actually participated as a student, as a graduate student in the Abrona conference. It was in '62. Is it true? Abrona conference. Is it?
Yeah,
Is it 62? Yeah. He participated in that conference and to learn. So he went to the time Harvard, having after studying in every sense stars and structure of stars and constitution of stars, after many very relevant volumes he had written and so on. So it's also interesting that he himself felt involved at that time in this new interest. So he felt the air some way. This is confirmation that it was an atmosphere, intriguing atmosphere. That of course he was easily captivated by the subject, but in any case it's proof of this.
So I would make a suggestion now to you, as I don't see any more urgent questions, so we can all take a quarter of an hour coffee break. At 5 o'clock, Professor Gutfreund will be there to give us a short introduction